Hi and welcome. Thank you for joining me today. Today we're going to talk about subsets of real numbers. So remember that a set of numbers is just kind of a list of numbers, and real numbers are really any of the numbers that you can think of. At least for now, they're pretty much everything we're going to be talking about as far as numbers this year. Later on, we're going to talk about imaginary numbers and complex numbers that are outside of the real numbers. But just for now, just think of these as the numbers that we'll be dealing with for the most part. Okay, so subsets. First subset. Remember, a subset is just a smaller set of those numbers. So our first subset is integers. And integers are all of the positive and negative counting numbers. So think of the numbers that you might use for counting, and it's all of the positive and negative ones of those. So I actually have them all listed here. You can't really tell that I have listed them all, but this little dot 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 means that it goes on with this same pattern forever and ever. So I'm really going all the way out to negative infinity here, to -3, -2, -1, 0, 1, 2, 3, and then so on to infinity again. The integers do have a special symbol. It is this letter Z with a double middle there. Okay, the next subset of real numbers is the natural numbers. And the natural numbers are just all of the positive integers. And we do have a symbol for the natural numbers. It is the symbol N right here. And again, notice the N has a double bar down the middle of it. And so notice it did say positive integers. So it doesn't include 0. So we start out at 1, 1, 2, 3, 4, and so on up to infinity. Okay, so the next one is whole numbers. And whole numbers include all the positive integers as well as 0. So, and we don't have a special symbol for whole numbers, but we can use the symbol of natural numbers and then include 0 in there. So, for example, 0, 1, 2, 3, and so on, repeating forever and ever. And rational numbers are any number that can be written as a fraction. And these are going to be fractions, repeating decimals are also considered rational numbers because we can write a repeating decimal as a fraction. And our symbol for that is this letter Q with the bars on the side here. So I can't list all of the rational numbers. However, we can maybe show some examples. So 1/2, 3/4, 6/1. Notice that 6/1, any whole number can be written as a fraction over 1, so it's a rational number also. 7/3, 0.50 repeating, 0.505050, and so on. That is a rational number also, because we could write this as a fraction if we wanted to. Okay, next is irrational numbers. Irrational numbers are non-terminating, non-repeating decimals. So for example, you might remember in your studies with circles, we have the letter pi. The letter pi stands for a number, and that's a Greek letter, by the way. It stands for the number 3.1415, so on. And it goes on forever. It never repeats. It's always changing, and so it's a really long number. A couple other examples like that are the number e, which we will be learning about later this year, and the number phi. This is another Greek letter, phi. It's the number of the golden ratio. So if you want to find out more about that number, just look up golden ratio and it will tell you all about it. So non-repeating, non-terminating decimals. Also, square roots of any numbers that are not a perfect square. So for example, the square root of 5 is an irrational number, or the opposite of the square root of 8 is also an irrational number. Okay, so in our chart here, I've made a chart to kind of help us visualize this a little bit more. Down here at the bottom we have natural numbers, and remember that included the numbers 1, 2, 3, 4, and so on up to infinity. Whole numbers included all the natural numbers plus 0, so that's why 0 is the only one in here. Think of this as a Venn diagram. So we have all of the natural numbers here, and we're just including the number 0 also within the whole numbers. And then integers just a little bit more, we have all of the opposites of all of the natural numbers. So that's why I've only listed those, because it also includes all of these. And then rational numbers, I've listed some examples of rational numbers around here. And then completely separate is irrational numbers, because irrational numbers do not include any of these. It's completely separate group. So I've put some examples here: pi, e, phi, square root of 2, opposite of the square root of 3, or even some of the cube roots also are irrational, like the cube root of 16. And just a quick note, the symbol for real numbers is an R with a double back on it. So if we are writing down and we want to say that we're talking about all real numbers, we can just include that symbol there. So, some example problems. Example 1, what is the most specific subset of real numbers that the opposite of square root of 7 belongs in? Well, since 7 is not a perfect square, it does not belong in rational numbers or natural numbers or any of those. So the opposite of the square root of 7 is an irrational number. Okay, example 2. List all of the subsets. So notice in this one it said the most specific, so we're just listing one if it says the most specific. If it says list all, we're going to find all of them that the particular number is in and list all of them. So list all of the subsets that the cube root of -8 belongs in. Well, if you might remember, the cube root means what number multiplied by itself 3 times. And so we have to think about what number times itself 3 times equals -8. Well, -2 times -2 is +4, times -2 again is -8. So the cube root of -8 is -2. So the subsets are, well, first of all, that belongs in the integers, because it is a counting number, but it's the opposite of a counting number. So it doesn't include, it's not a whole number, it's not a natural number, but it is an integer. And remember, if we wanted, we could write this as a fraction, so it is a rational number also. Next problem, true or false? 0.01, 001, 0001, 00001, and so on, is a rational number. Well, remember, in order to be a rational number, we have to be able to write it as a fraction. And so if we continue this pattern is constantly changing. So we could not write this as a fraction at all. So the answer would be false. There is no set of digits that repeat, so there is no way to write the number as a fraction. Okay, so ordering real numbers. Remember, one thing we can do is order numbers, decide which one is bigger or which one is smaller. And real numbers can be listed in order or placed in it on a number line. So for our next example, graph the following numbers on a number line: -3, square root of 7, 1/3, and 13/4. So we're going to put all 4 of these numbers onto our number line here. So the first thing I did is just made a number line, and I did some calculations over here on the side. So the square root of 7 is about 2.64. Now this is an irrational number, so I can't write exactly what it's equal to other than as an approximate decimal. 1/3 is equal to 0.333 repeating, so it's about a little bigger than 0.3. And 13/4 is about 3.25. So I took each of those. Notice here I put a dot over the -3, but I also labeled -3 here. Because remember, when we're graphing points, it's important to label our points. So I put -3 above it here. Over here is the 1/3, so I put a dot at about 1/3, and I did label it as 1/3. Okay, 2.64, that's a little bigger than 2.5, so I put it a little to the right of 2.5. And again, I labeled it with the square root of 7. And then 3.25, I put it about a quarter of the way between 3 and 4, and I did label it as 13/4. Okay, last example. Compare each pair of numbers using greater than, less than, or equal to. So for A, -1/7 compared to -1/5. Well, -1/7 is about -0.143, and -1/5 is about, or is equal to, -0.2. So we have to think about which one of these is bigger. Now, it might be tempting to say that the 1/5 is bigger than the 1/7 because this number does look bigger. But remember, when we're talking negative numbers, we have to think about which one is more to the right. And so the one here that is more to the right is the 0.143. So 1/7 is greater than 1/5. So remember, greater than goes that way. Remember, if you think about it from elementary school, the alligator always wants to eat the bigger number. I guess that's an easy way to remember it. So we have the mouth opening up towards a bigger number here. Okay. Next one, B, 0.6 repeating or 2/3. Well, if we rewrite this is 0.666 repeating, and 2/3, if you are not sure and you want to type that into a calculator, go 2 divided by 3, and it does say 0.666, and so on. Now, at some point it might say 7 is the last digit, but remember, since it's repeating, it's rounding that last digit up, so it really is 0.666, and so on, repeating. Okay, so those two happen to be equal. Okay, and C, 0.024 compared to 0.025. Well, again, we have to think of which one is farther to the right. And so this case, since they're both positive, the one that looks bigger actually is bigger. So 0.024 is less than 0.025. And that is it. I hope that helps you out today, and good luck, and I'll see you next time.